So I just spoke about temperature dependence. Okay, what about pressure dependence of... one thing I should say here is that reactions and reactivity is very sensitive to temperature, as we said. So there's you increase the temperature from 700 to 765. There was a factor of 40 increase in rate constant in that temperature range, okay? So the kinetics is very, very sensitive to temperature, and it's exponentially dependent on temperature, okay? It's not exponentially dependent on pressure. It's more linearly dependent on pressure. So and typically, and we'll see in a minute, okay, we have PV is equal to nRT, okay? So we have P over RT is equal to N all over V, okay? Which is equal to concentration, okay? N over V is concentration. So if we're at a constant temperature, okay, and we increase the pressure, the concentration will increase linearly, okay? And remember, the rate of reaction, if we have A plus B giving products, okay, the rate is equal to the rate constant times the concentration of A to the alpha and B to the beta. And let's just assume it's first order in each one. So we can have the rate will be equal to the rate constant, second order rate constant, times A to the power of 1 and B to the power of 1. It's not necessarily true, but let's just say it is, okay? Then if we increase the pressure, right, by linearly, there's going to be a linear increase in the rate. Why? Because the concentration of A will increase linearly, and the concentration of B will increase linearly. Okay, so there'll be that increase. Okay. Whereas for temperature, so that's sort of the pressure. That's what you would normally expect with pressure, right? That there would be this linear increase because you increase the pressure, you're increasing the concentration of the species. If the concentration of the species are increasing, then the rate will increase, okay? And that's the point, okay? So in some reactions, a third body is required for the reaction to occur, okay? So we have this general equation again, A plus M, a third body, gives B plus C plus M. This is a unimolecular decomposition, but it has to collide with a third body for the reaction to occur, okay? M represents collectively all of the atoms and molecules in the reacting gas, okay? And it's given by M, the concentration of N is equal to P over RT, okay? As I just wrote on the board there, okay? So, but some colliders may react more efficiently as third bodies than others, okay? So for instance, often relative rate coefficient. So in some arbitrary reaction here, collision partner CO has a relative rate coefficient of 1. But that for H2 is 1.3, CO2 is 2, and H2O is 6. Okay, so what does that mean? It means when the code is doing the calculation, it'll take the mole fraction of water, for instance, and multiply its mole fraction times 6. So the M that we calculate will be slightly bigger than the total pressure in the system, because if we have a lot of water in the system, its concentration is actually considered to be 6 times higher than it actually is, because it's 6 times more efficient in colliding. But that's a way of the code calculating the increased rate of reaction. Okay, so if we define everything relative to CO, okay, then we have to include these collision efficiencies to get the right rate of reaction. Does that make sense? I hope I've explained that fairly, as clearly as it's understood. Okay, so, but if we go here, if we have A giving us products, right? In this A plus M giving us products, right? So we plot rate constant on the y-axis versus log of the concentration of M on the x-axis. If everything was perfect, the rate of reaction should increase to infinity, assuming that we would have infinite concentration, right? Then the rate constant would go to infinity, but it doesn't, right? It reaches K infinity, a high pressure limit, okay? So the rate of reaction has, and typically the limit is about 10 to the 14 per second. That's a good rule of thumb for the limit in rate of reaction, about 10 to the 14 per second, right? So we have a limit, a high pressure limit in the rate of reaction. So if we plot rate constant then on the y-axis versus log m, we see, okay, so the rate of reaction, the rate constant does increase linearly. So K0, this is the low pressure rate constant, increases linearly for low concentrations of M. But as M concentration gets higher, it starts to asymptote out and then reaches this high pressure limit at high concentrations of M. Okay? And so the true rate constant of reaction is not K0, it is K0 at very low concentrations of M, it's K infinity of high concentrations of M, but it's something in between those concentrations. Okay? And we have to be able to resolve this. So the imaginary point of intersection between the low pressure rate constant and the high pressure limit rate constant, the point of intersection occurs at a critical concentration of M, MC. Okay? And this is the concentration of M where the low pressure rate constant and high pressure limit rate constant would meet. Okay? It's the concentration, the third body concentration at which those rate constants meet, intersect. Okay? So if we then look at it, a dissociation reaction involves 3 steps: collisional activation to form unexcited molecules, collisional deactivation, and unimolecular fragmentation. Okay, we'll look at this. So here we have AB, a molecule. Let's just say propane, for argument's sake. Okay, C3H8. It reacts with a third body. It gives excited propane plus M, and then that excited propane can deactivate to give back propane plus M again, or it can go on to give us ethyl and methyl radical, right? Okay, so we can have propane essentially going on to give us ethyl and methyl radical. Okay, so these reactions involve an energy-rich intermediate species donated by AB star. Okay. So the rate constant for dissociation then of AB is equivalent to -1 over the concentration of AB times the change in concentration of AB with respect to time. Okay? And the rate constant for recombination is equivalent to +1 over the concentration of A times 1 over the concentration of B times the change in concentration of AB with respect to time. So applying the steady state of approximation to the change in concentration of AB star with respect to time, and that's equal to 0, okay, to the concentration of AB star, we can show that the rate constant for dissociation is equal to the rate constant of reaction 1 times the concentration of M. Reaction 1, if we go back, is here, rate constant 1 is AB plus M becoming chemically activated to AB star. Okay? So the rate constant for dissociation is equal to K1 times M times K2 all over K2 plus the reverse rate constant for reaction 1 times M. Okay? And then rate constant for recombination is equal to the reverse rate constant for reaction 2 times the reverse rate constant for reaction 1 times M all over the rate constant for reaction 2 plus the reverse rate constant for reaction 1 times M. Okay? So then the rate constant for dissociation all over the rate constant for recombination, I think this is simpler, is rate constant for reaction 1 all over the reverse rate constant for reaction 1 times the rate constant for reaction 2 all over the reverse rate constant for reaction 2. And that's equal to the concentration of products all over reactants. Okay, concentration of A times the concentration of B all over the concentration of AB at equilibrium. And that's equal to the equilibrium constant Kc. Okay, so we have then the rate constant for dissociation and the rate constant of recombination have these expressions here. The limiting rate coefficients are the low pressure limit. So the limit when m goes to 0 for dissociation is equal to the rate constant for reaction 1 times the concentration of m. Okay? And that's why this graph here, we have, it's linear here at very low concentrations of m. Okay? So it's equal to K1 times the concentration of m, essentially, is what we're seeing here in this period. If I go back, I should copy that forward. Okay. Okay, so it's equal to K1 times the concentration of m. Okay, so and the limit, the low pressure limit as m goes to 0 for the rate constant for recombination is equal to the reverse rate, the rate constant for the reverse of reaction 2 all over the rate constant for the forward rate constant for reaction 2 times the reverse rate constant for reaction 1 times m. Okay, you can derive those. Okay, and so if we look at this, the high pressure limit rate constant then is equal to K1 all over K minus 1 times K2, and the high pressure limit for recombination is equal to the reverse of reaction 2. Okay, the reverse of rate constant for reaction 2. Okay, so here then, if we plot m over the critical concentration of m, that's equal to the low pressure rate constant divided by the high pressure rate constant, the high pressure rate constant times the concentration of m. Okay, and that's equal to x. So m over mc is actually equal to x, and that's called the reduced pressure. Okay, it's just what that relationship between the whatever concentration of m you have and the critical concentration of m, that's called the reduced pressure. Okay, so we have the rate constant then all over the high pressure limit rate constant. That's equal to the low pressure rate constant divided by the high pressure limit rate constant divided by 1 plus K0 over K infinity. Okay, and that's equal to the concentration of m divided by the critical concentration of m all over 1 plus m over mc. So that's, we can say, is equal to x all over 1 plus x, or we write it as equal to the reduced pressure divided by 1 plus the reduced pressure. And this is the expression in Lindemann form for this curved fit in the transition going in rate constant from the low pressure limit rate constant to the high pressure limit rate constant, in determining what the rate constant is along the curve here. Okay, that's the Lindemann format. Okay, so where am I? So we have this expression here in general then. Okay, we have the rate constant. If I go back for a second, we had the rate constant is equal to K infinity times the reduced pressure all over 1 plus the reduced pressure. Okay, if we just bear that in mind. So we have the rate constant is equal to K infinity times the reduced pressure over 1 plus the reduced pressure. Okay, but there's another term then that we use. It's called F. Okay, and that's, F is the broadening factor and is unity when we're in the Lindemann form. So when we're in Lindemann form, F is 1. Okay, and we have this relationship. The rate constant is equal to the K infinity times the reduced pressure all over 1 plus the reduced pressure, where the reduced pressure is m over the critical m, MC. okay? Okay, so we can say the reduced pressure is equal to K0 times m over K infinity. Okay, so whichever way you want to look at it. So we have K infinity has this expression here, and that's the low pressure. So this is the high pressure rate constant and the low pressure rate constant. And then we get the rate constant between the limits is determined in this way. Okay, so this is the general expression for the calculation. But if we're in the Lindemann form, F is 1, okay? And that's how the rate constant is then determined. Okay, so, but we have not the we have another form, and it's the Troe format, not just the Lindemann format, but the Troe format. The Troe format, the broadening factor is given by log of F is equal to 1 plus the log of the PR, reduced pressure, log PR plus C all over N minus D log the reduced pressure plus C all squared, and then this term it's 1 over this term, basically, okay? And times log of F cent, okay? So this is a very complicated looking expression, and it is, okay? Because we have C is equal to this expression here, N is equal to this expression here, and D is equal to 0.14. Okay? And this, we have to include these numbers in our calculation to get log F. But not only that then, but we have log F cent. Okay? And then log F cent is 1 minus A e to the minus T all over T triple star plus A e to the minus T all over T 1 star plus the exponent of minus T 2 star all over T. Okay? And so typically in the Troe format, what happens is the 4 parameters A, T3, T1, and T2 are all provided. If we're given A, T3, T1, T2, we can calculate F cent. F cent is then put into this equation here, into this, and into this, so we can calculate C and N, and we know D, and then we can calculate log F. If we calculate log F, we can get the broadening factor F, and then the rate constant is equal to K infinity times the reduced pressure all over 1 plus the reduced pressure times F at each M. Okay? And then when you do all that, okay, you get a fit K0, and this is K infinity, that may be less than, it's not quite right. Okay, you can see there. Okay, but this is, sorry, I took this plot from the Kempkin 2 manual. So if you go online, you can download the Kempkin 2 manual, and it may help you a bit by looking at this. So there's another fit too called the Stewart fit that's in there. So you can, I'm not going to talk about it today. It's enough to talk about Lindemann and Troe, and it's complicated enough. All right, but what I want to highlight here is that the rate constant does not increase linearly with pressure or with concentration of M, right? There's a low pressure limit rate constant, there's a high pressure limit rate constant, and what we have to do is calculate the curvature in between to get the rate constant correct, okay? And the Lindemann format and the Troe format are ways to try and do that, okay? So I just lifted this plot today, actually, because it's not in the notes that I provided you, okay? So you can just have a look yourselves, and I've edited the notes slightly, okay? So you can have a look at that, okay? If you write to me and ask me, I'll send you the up-to-date notes on this, okay? No problem, just send me an email, okay? So another way that we do this now, though, and more, and actually even for rate constants where we had Troe fits before, we've changed to using P-log fits. And this is much more accurate, okay? And so let me just show you what we do, basically. Here we have methyl plus H giving methane. So it's methyl plus H plus M giving methane plus M. And Stephen Klippenstein would have calculated this, the high pressure limit. Here it's, well, it's about 3 times 10 to the 14. Remember I said 10 to the 14. Well, it's 3 times 10 to the 14 here, is these high pressure limit, okay? But here's the rate constant at 0.01 atmospheres. Here it is at 1/10 of an atmosphere. Here it is at 1 atmosphere, 10 atmospheres, 100 atmospheres, and then the high pressure limit, okay? And you can see that's the pressure dependence calculated. But what if I want to calculate a rate constant like halfway at 5 atmospheres, okay, in here? Or what if I want to get it at 1/2 an atmosphere? Well, there's a way that we can interpolate and go, you know, so we have, here we have the 0.1 atmosphere, here we have 1 atmosphere. We can get 1/2 an atmosphere halfway in between that. And we can get it quite accurately using the P-log format, okay? So the P-log format, what it does is, it takes the rate constant between 2 pressures, right? And then you can interpolate a rate constant in between those 2 pressures, right? And what it does is you say, okay, log of the rate constant between the 2 pressures is log of the lower rate constant plus the rate constant at the higher pressure, okay, minus the log of the rate constant at the lower pressure, okay, times the log of the pressure that you're looking for minus the log of the lower pressure, log of lower pressure divided by log of the higher pressure minus the log of the lower pressure. And what you're doing here is you're calculating, to calculate the rate constant of any pressure then, the log of the rate constant is interpolated as a linear function of log of pressure, okay? And you're interpolating a rate constant between 2 pressures, right? So, and oftentimes when Dr. Klippenstein or other people report rate constants, they report rate constants over a range of pressures, something like this. But then we can use the P-log format. We just specify. So what we do then is we say, okay, P-log, and then we specify, okay, at 0.01 atmospheres, here's the rate constant. At 0.1 atmosphere, here it is. And then the code, wherever you're at in your calculation, will interpolate accurately at the pressure that you're actually at for your calculation, okay? Which is a nice way of doing things. And it doesn't much matter, actually. The Troy formalism produces a good fit for single well systems, like this one, methyl plus H giving methane, right? You actually get a good Troy fit. This one was a bad one, okay, presented here. It doesn't look great, okay, because it's not reaching the high pressure limit, and it seems to be below the low pressure limit, okay? So it's not doing a good job there, okay? So that's a bad example of a Troy fit, okay? But typically, it was the best fit that we had to account for pressure dependence back in the day, okay? But now we can do much better. And as I was saying, for methyl plus H, it actually could do this quite accurately. But for multi-complex systems, so here, ethyl plus O2 can give you ethyl peroxy, but it can also give you ethylene plus HO2, right? So there's two major product routes here. And in that case, the multi-well system, the Troy formalism doesn't work that well. But the P-log formalism works very well, okay? Much better for these multi-well systems. So if you have the choice, okay, so it can form ethyl peroxy, it can form C2H4O2H, it can give you ethylene plus HO2, or it can give you the cyclic ether plus OH. There's 4 different channels here, right? Not just one, okay? And so using the P-log fit, you can account for the accurate rate constants as a function of pressure for all 4. Because now you have 4 competing pathways at every pressure and temperature, okay? So you need to have really accurate predictions, okay? I'm not quite sure where I'm going with this. I'm just going back to this diagram. I keep kind of using it because I like, to consider, okay, we're talking about kinetics on this side and equilibrium on this side. And now I'm finally going to show you actually the connection between thermodynamics and kinetics, right? And they're not mutually exclusive, okay? That they're actually interlinked, okay? And here it is, okay? So we have, as I said, there's an equilibrium A to B. So it starts out at the very early stages, and all we have is A goes to B. And we have no B going to A because the concentration of B is so small that the rate of reaction is very low, okay? But eventually in time, the B accumulates, and now A can give B and B gives A, and so at some time here, about there, the system reaches equilibrium and the rate of formation of B from A is equal to the rate of formation of A from B. Did I say the same thing there twice? The formation of B from A is the same as A from B. And at that stage, the system is at equilibrium. But it's the rate of the forward reaction then is equal to the rate of the reverse reaction, right? It's not some magic. It's just that B concentration is accumulated, and now it's high enough in concentration to start giving us back A, okay? Not just start, but it continuously. And so now we have the cycle where A goes to B, B goes to A, and the concentrations of the two species don't change anymore. All right, so the rate in the forward direction is equal to the rate constant in the forward direction times the concentration of A, and the rate in the reverse direction is equal to the rate constant in the reverse direction times the concentration of B, okay? And at equilibrium, the rate in the forward direction is equal to the rate in the reverse direction. So the rate constant in the forward direction times the concentration of A at equilibrium is equal to the rate constant in the reverse direction times the concentration of B at equilibrium, okay? And we have then K forward, so K forward over K reverse is equal to the concentration of B at equilibrium divided by the concentration of A at equilibrium, and that's equal to Kp, right? I'm writing it as concentration, but actually it should be partial pressure, right? It should always be partial pressure. So when we talk about equilibrium in kinetics and combustion kinetics, it's always Kp, okay? Now, not always, but oftentimes. So if delta N is 0, then Kp and Kc are equal, okay? If the change in number of moles is 0, then Kp and Kc are equal. If not, then Kp is equal to Kc times RT to the delta N, okay? And so you can calculate Kp from Kc, but you have to multiply by RT to the delta N, okay? And you would have probably been shown that at under. Okay, so Kp is equal to Kc as delta N is equal to 0. Okay, so we have K forward is equal to A forward. We could have T N forward e to the minus E forward RT, okay, in the non-Arrhenius expression. But let's just assume the Arrhenius expression. And here we have K reverse is equal to A reverse e to the minus E reverse over RT. Okay, so K forward over K reverse is equal to Kp, and that's equal to A forward over A reverse times the exponent of minus E forward minus E reverse over RT. So we get all of this from kinetics. Is that all right? There's nothing unusual there. It's fairly straightforward. Okay. From thermodynamics, though, we know that Kp is equal to the exponent of the change in Gibbs free energy for a reaction, the standard Gibbs free energy for a reaction all over RT. Okay? So we have that's equal to the standard change in entropy for a reaction over R times the exponent of the standard change in enthalpy for a reaction over RT. Okay? So we have Kp is equal to E to the delta S over R times E to the minus delta H over RT. Okay? But we know that Kp is equal to A forward over reverse times the exponent of minus E forward minus E reverse over RT. So now we can say A forward over A reverse from kinetics is equal to the exponent of the standard change in entropy for a reaction over R from kinetics, or from thermodynamics, I should say, and that E forward minus E reverse from kinetics is equal to delta H, the standard change in enthalpy for reaction. Okay? So that's the link between kinetics and thermodynamics. Okay? And it's really nice, I think it's a really nice way of showing it. Okay? So, in other words, the frequency factors are related to entropy change, right? And the activation energies are related to enthalpy change. Like I was saying yesterday with the kinetics when I want to go across the theater, okay? I'm not going to go anywhere if I don't start to move, okay? My frequency. So my frequency is increasing, and if I run, it's at its highest, as fast as I can run, okay? And then you'll have an energy barrier. So I walk here, no problem. I reach the podium, I'm in trouble, right? Activation energy barrier. Okay. Okay, sorry. And here's a problem. Okay, for the reaction trans to 6-perfluorobutene, the measured rate constant is 3.16 times 10 to the 13 times the exponent of minus 31,030 all over T, so it's an activation temperature. Given that the delta H is 3.42 kilojoules per mole and delta S is minus 2.03 joules per joule Kelvin per mole, calculate K reverse at 750 Kelvin. Okay? So we know A forward over A reverse is equal to the exponent of delta S over R. So A reverse is going to be A forward times the exponent of minus delta S over R. Okay? It's just the 1 over plus delta S over R. Okay? And E forward minus E reverse is equal to delta H. So E reverse is equal to E forward minus delta H. Just be careful with the units, but so we get E reverse is 254.6 kilojoules per mole. And we can get A reverse is just A forward is 3.16 times 10 to the 13 times the exponent of plus 2.03 all over A.314. Okay? And that way we can get the K reverse. And from that, we can actually get the rate constant at 750 Kelvin. Okay? Because we'll know A and EA. Okay? I don't know the answer. Okay. Here's one that I'm going to come back to later in the week. I'm not sure if it's tomorrow, probably Thursday, right? But it's, well, I'll show you, I'll talk about it now, right? But, so we have this equation here. And let's say we have this reaction, A plus M gives B plus C plus N. Okay? So we have let's look at the frequency factor. Okay? So the frequency factor, A forward over A reverse, depends on the exponent of delta S over R. But the standard entropy change for a reaction, okay, it should be delta S 0 all over R. Okay, is that all right? Okay, so that's equal to the entropy of B plus the entropy of C minus the entropy of A divided by R. Okay, that's all right with everybody? Okay, so that's equal to the exponent of the group contributions to the entropy of B minus R log the symmetry of B plus the group contributions to the entropy of C minus R log the symmetry of C minus the group contributions to the entropy of A minus R log the symmetry of A. And all of those values divided by R. Right, that's okay. So that's equal to then the exponent of the group value contribution to the entropy of B plus the group value contributions to the entropy of C minus the group value contributions to the entropy of A, all divided by R, minus the log of the symmetry of B plus the log of the symmetry number of C minus the log of the symmetry number of A. Okay? So this is equal to the exponent of the change in entropy of the group values of the species all over R times the symmetry of A divided by the symmetry of B and C. Okay? So let me just talk about this for a second, because this is important. And we come across it again on Thursday, and I'll say it again, but this is important here now, right? So let's look at neopentane. That gives us TC4H9 plus CH3, okay? Or if we look at N-pentane, that can give us NC4H9 plus CH3. I hope you understand. I'm not going to draw it because it's just linear. Okay, so what's the symmetry number of neopentane? Pardon? No. This is fun now, actually. Okay, so let's do it together. Okay, 3 times 3 is 9, times 3, 27, times 3, 81. Okay, so it's 81 times something. Okay, so let me just, I'm going to go away for a second, right? And I'm going to come back with methane. What's the symmetry number of methane? He says 4. 4. Everybody happy? 4? You're all wrong. It's 12. Okay, it's 12. It is fourfold symmetry, but you're in three-dimensional space, right? So it's 4 3s are 12. Okay, that's why I wanted to do methane, because the symmetry number of methane is actually 12. Symmetry numbers are not easy to get right, okay? But the symmetry number of methane is 12. So then, if that's the case, we have 81 from the 4 methyls times 12. Is that all right with everybody? That's why I did methane, okay? And now, what's the symmetry number of neopentane? It's 972. Okay, 972. Okay, it's huge, right? And now, but what did I say the symmetry number of terbutyl was yesterday? Remember, in relation to isooctane. It's 3 times 3 times 3 is 27 times, think of the umbrella, and you've got 3 methyls if you rotate through 120. So again, there's another 3. So that's 81. And this is 3. Is that all right with everybody? Right? So we have 972, 81, and 3. Okay? Now let's do N-pentane. The symmetry number of N-pentane is 18. All the alkanes are 18. Okay? It's 3 times 3 is 9, and then there's a twofold symmetry on the central carbon atom, because if you look left and right, it's the same environment. So it's 18. 2 times 9. All right? What's the symmetry number, though, of C4H9? Sorry, I should maybe draw it. C4H9 is this. So what's its symmetry number? 6. 6. Everybody happy? 6. And what's the symmetry number of methyl? 3. Okay. Now, have a look at the numbers that I've written down there. Okay, and what's sticking out a mile is neopentane is 972, right? N-pentane is only 18. Okay, so let's now do our, here, the group value factor. We can't control that. Whatever comes out from the groups comes out from the groups, right? Times the symmetry number factor in the rate constant for reaction. Okay, so remember now the A forward over A reverse. So the rate constant, right, is going to be influenced by the exponent of the change in entropy of the group values divided by R times the symmetry number of A divided by the symmetry number of B plus times symmetry number of C. Okay? So let's do it for neopentane, giving us terbutyl plus methyl. Okay? I'm just going to rub this out, if you don't mind. And what do we get? We're going to get 972 divided by 81 times 3. So that's 243. And what's 972 divided by 243? It's 4, isn't it? I think it is anyway. Okay? Right. And then we have 18 divided by 18. So what's that equal to? 1. Okay. What is this? Okay, so let me, I'm kind of confusing you now, right? So let's look at it this way. Okay. If I'm leading up to something, right? And I mightn't have introduced it very well, but here we have neopentane and here we have N-pentane. They're the same size molecule, right? Both of them have the same molecular formula, C5H12, right? One gives us TC4H9 plus methyl, the other one gives us NC4H9 plus methyl. So the products are about the same, right? They're different isomers, but they're the same size, okay? And so actually, and I'll be talking about this later in the week, right? If we take a moiety, so the way I would look at this reaction is I would estimate the rate constant in the reverse direction. It's methyl plus terbutyl giving me neopentane, right? So I would put the rate constant into Chemkin as methyl plus terbutyl giving me neopentane. And that would have a rate constant of 10 to the 13, right? That's my guess, right? It's pretty good, right? But it's about 10 to the 13, right? And that's just the frequency factor in the reverse direction. Now I have A reverse. So how do I get A forward? I know that A forward over A reverse is the exponent of delta S over R. Is that all right? A forward over A reverse is equal to delta S over R. If I go, sorry, it's not on that slide. A forward over A reverse, sorry, is equal to the exponent of delta S over R. Okay? So if I know A reverse, so in both cases, A reverse is 10 to the 13. So what's A forward? If I go back, A forward is going to be A reverse times the exponent of delta S over R. Okay, so A forward is going to be A reverse 10 to the 13 times the exponent of delta S over R. Okay, but so the delta S that I calculate in this case, right, is 4 times bigger than the delta S I calculate in this case, assuming that the group contributions are about the same. So let's just assume that. Okay? There won't be, but like hand waving, they're about the same. Okay? What does that mean? It means for neopentane, because of its high symmetry number, right, it will undergo unimolecular decomposition 4 times faster than N-pentane, all other things being equal. Right? And that's actually what we see. Okay? Neopentane undergoes unimolecular decomposition much faster than N-pentane and isopentane, right? More than you would think. Why? Because of its high symmetry. And it makes sense, right? Look at its symmetry. It's very ordered. What does the world want to do? Become disordered, right? And with Donald Trump and the likes, it becomes disordered very quickly, right? Shouldn't be talking politics, but anyway. So anyway, the world is heading towards disorder, or nature likes disorder, right? It wants to become disordered. So if we start with something that's highly ordered, it wants to become more disordered. How does it do that? By having a frequency factor that's 4 times bigger, right? So the entropy demands it, that it will decompose just on a frequency factor, right? It'll be 4 times faster to decompose than N-pentane, okay? And that's pretty cool, right? And it's just nature coming out, okay? And it's because A forward over A reverse is equal to E to the delta S over R, okay? So I show that on Thursday in the slide, but there it is. I've shown it there, okay? And so that's why I've done this out in the way I have, okay? Because the group value factor may or may not be very different, but you can see that the delta S gives you a factor of 4 just because of the entropy, okay? And that, I just wanted to highlight that, okay? So here we have a reaction profile diagram. And what is it? It's a reaction coordinate diagram, basically. And what we show here is the reactant and product identity, okay? So this is typical. So you could write here, for instance, C2H5. And then here you could write C2H4 plus H, okay? And this is important, actually, for later in the week. So if we look at this reaction C2H5, it has to overcome a large energy barrier and reach a transition state and then go to products C2H4 plus H, okay? But actually, this barrier varies depending on delta H of reaction, okay? But typically the reverse barrier, the one in the exothermic direction, is constant. So the barrier for H addition to ethylene, or H addition across a CC double bond, stays about the same. Now, I'll give you more details of that later in the week, okay? So, and if it does, then we can just, what we normally do is we'll enter a rate constant, or estimate a rate constant, in the reverse direction, in the exothermic direction, where we don't have to consider delta H of reaction. We let the code consider that itself, okay? Because this delta H, what I'm saying is, look, and you could equally write NC3H7 gives C2H4 plus CH3, right? Again, now C2H4 plus CH3 has a different activation energy barrier than C2H4 plus H. That's about 7.8 kilocalories per mole. But again, you're putting in 7.8 for this barrier. And then if you had propene plus methyl giving you butyl radical, again, this energy barrier in the reverse direction would be the same. So if I have a C double bond C and a carbon atom adding to the terminal carbon atom in a C double bond C, the activation energy is always about, or almost, 7.8 kilocalories per mole, regardless of what it is. But if it produces N-propyl radical, N-butyl radical, N-pentyl radical, the delta H is going to be different. Okay, so this piece is going to be different all the time. So when we look at reactions like this, we look at them in the exothermic direction, the reverse direction, and then let the thermodynamics calculate the rate constant in the forward direction. That's what I'm trying to say. Okay. That wasn't the reason of this. It's just to show how we can depict what's going on. So let me just explain it more readily by this diagram here. So what we have is called an intrinsic coordinate, reaction coordinate. Okay? So what we have, what I'm showing here is the energy calculation for the reaction, the hydrogen atom abstraction of a hydrogen atom from acetone by OH radical. Okay? This is one that a postdoc of mine did, we'd say 10 years ago or more. Okay? So what we start off is to say, okay, this is the relative energy to the reactants. So I don't know what the energy of OH is, and I don't know what the energy of acetone is, right? Okay? But whatever their energy is, we say that relative energy is 0. Okay? So what happens, right? So if I start off, OH is out here in the distance, away from acetone, then there's no energy of interaction. Okay? But if the oxygen atom comes down close to this hydrogen atom, what's it going to do? Yeah, it's going to be attracted to it, right? Because and it would like to form water, ultimately. And that's one of the main exothermic reactions in combustion. So remember, why do we burn things? To get water and CO2. And when we get water, we get a lot heat released, and we take that energy and we do whatever we want, use it for. And when we oxidize carbon into CO2, we get even more heat, and we use that, okay? And hence addiction to coal. So anyway, so the intrinsic reaction coordinate then is telling us the proximity of the acetone to the OH, okay? And what you'll see is, when I run this video, is that the energy, and it's hard to do it because it goes fairly quickly, so you just have to, I'll run it a couple of times, right? But what you'll see is that the oxygen atom will dip towards this hydrogen atom, and then the energy will go up, right? Why? Because this hydrogen atom starts to be pulled away from this carbon atom, and it starts to break the CH bond. But to do that requires energy, right? And the more that this hydrogen atom is pulled towards this oxygen atom, the stronger is the pull back and the resistance until we reach the transition state. And you'll see when it reaches up here, this CH bond breaks, and then the whole thing relaxes down, and it becomes more stable at the end. And why is it more stable? Because we produce water, and it's exothermic. Okay? So if you just look at this diagram, it sort of explains what it's doing. Okay? What the reaction coordinate actually is telling you. Okay, so if I just play it. Okay, so look at the point on the graph and look at what's happening above, and you'll see. You see the hydrogen, and then it moves over to the OH. Okay? And that depicts this reaction coordinate. So each point along the curve there is the energy that the system has. So you see the hydrogen is being pulled away, and eventually it breaks the CH bond. But to break that CH bond you have to put energy in first before you get the energy back out when it relaxes back to water and the acetonal radical. Okay, so that's what that reaction coordinate diagram is depicting. Yeah.
So initially, when the energy is increasing, is it effectively exothermic?
Yes. Yeah. So you have to put that. You have to invest that energy to break the bond so that, and you get it back out and more besides at the end. So you have to light the fire at home before you burn the wood or whatever it is, you're burning the coal or whatever it is, and then you get it back out, okay? So it's similar. Okay. So I just like that shows that. Another thing then is, and just to explain this, so you've heard of a catalyst, right? What does a catalyst do? It essentially just lowers the activation energy of reactions, okay? So here we have the reaction coordinate. Here now we're actually looking at it in the exothermic direction. So we're putting less energy in, and then we get more energy out, okay? And here we have delta H of reaction down here, okay? But actually, if we look at it, initially, for this reaction to occur, the energy barrier is 198 kilojoules per mole, okay? But if we add some iodine as a catalyst, it lowers the activation energy to 134 kilojoules per mole. So it follows the blue curve, not the magenta curve, right? So why is that? So there's a modest reduction in the energy barrier. Well, it's not modest, it's 64 kilojoules per mole, right? But there's a massive increase in the rate of reaction. And at 773 Kelvin, the catalyzed reaction is it's actually 21,000 times faster, right? How do I calculate 21,000 though? Where do you get that from? Yeah, well, the difference, so what do you do? In the first reaction, or K, we say A, or 1, is equal to A EXP minus 198000 all over A.314 times 773. And I'm doing this deliberately to kind of get you used to dealing with kinetics and rate constants and what they actually mean, okay? And then KB is equal to A EXP, well, sorry, I should say, this is T, would say EA1, maybe, and this is EA2, okay? Minus 134,000 all over A.314 times 773. So what's the difference actually? The difference, K for EA1 and K at EA2 is equal to the exponent of minus EA1 minus EA2 all over RT, which is the difference, which is the exponent equivalent to the exponent of minus 64000 over 8.314 times 773. Okay? And if you do that calculation, you'll get 1 over 21,000. It'll be whatever that is. And then, so you get the inverse of that. That's the difference, okay? But can you see, you know, when the activation energies are different, it's the exponent of whatever the difference is all over R, and then whatever temperature you're at. So it's going to be exponentially dependent on the activation energy and the temperature, right, simultaneously. So you have to be careful, because an activation energy difference might make a big difference at low temperature, but mightn't make much of a difference at all at high temperature, okay? So you have to take both into account, okay, when you're doing that calculation. All right, so actually, because of this reduction, and how does that happen? So basically, if you add iodine, what happens is, you see you have CH3CHO. You haven't much choice here. You can break a CC bond, but that takes 340 kilojoules per mole. You can break a CH bond, but that's even worse. That's 420 kilojoules per mole. But if you add iodine, the II bond is only 153 kilojoules per mole. So if you add I2, you can break the II bond by only putting in 153 kilojoules per mole of energy. Then you get I radicals, right? I radicals then can go in, abstract a hydrogen, and you get HI, okay? And then CH3 plus CO. And then CH3 can abstract a hydrogen atom from here, giving methane plus CO. Okay? So that initial generation of radicals is precipitated at a much lower or much faster rate because of the low energy barrier to break the II bond, generating radicals, which starts the reactivity for you. Okay? And that's why. So this catalyst, it actually, the I2 gets renewed, gets generated back, but it essentially lowers this barrier. Okay? And that's lowered because of the low bond association energy to break the II bond. Okay. Okay, and we can sometimes then, yesterday I said this and I just want to show it here. Okay, we can get thermochemistry from kinetics. So for instance, it's known, and I showed you, if you, to the reaction C2H6 giving 2 methyl radicals, that activation energy is measured, and how would you measure it? It's 368 kilojoules per mole. How would you go about doing that? Well, you could use a bomb calorimeter, for instance. Sorry, I think that's what you're saying, right? You could use a bomb calorimeter to get it, okay, and you get the heat of formation of ethane, and through that you can measure it, okay? Or what you could do is just perform the reaction, right? And then measure the rate constant at different temperatures. And then what you can do is plot log of the rate constant versus 1 over T, and you'll get an activation energy dependence. And that'll be 368 kilojoules per mole. Okay, that might be a roundabout way of doing it, but that's a way of doing it. Okay? But we can determine that. It's 368 kilojoules per mole. If we know that, we're sort of a lot of the way there. Why? Because the activation energy in the forward direction to generate 2 methyl radicals is 368 kilojoules per mole. That in the reverse direction is 0. So the activation energy for radical-radical addition, typically we take as 0. Radicals like to recombine to give a stable species, and with an activation energy of 0. Okay? So if that's the case, then we have delta H reaction is equal to E forward minus E reverse. But what is the reaction? It's breaking the CC bond. So the bond association energy in ethane is 368 kilojoules per mole. That's the BDE, we say, okay? Anyway, so we now have the delta H reaction is equal to, but what is the heat of reaction? It's 2 times the heat of formation of the products minus the heat of formation of the reactants, right? So that's equal to, so the heat of formation of a methyl radical then is equal to delta H reaction plus the heat of formation of ethane, all divided by 2, right? So the heat of formation of ethane is, is known from a bomb calorimeter, I should say, right, as minus 85 kilojoules per mole. Okay, we can get that from bomb calorimetry, okay? Then the heat of formation of a methyl radical, we can now calculate. It's 368 minus 85 divided by 2, and it's 141.5 kilojoules per mole. Okay? So if we did a series of reactions where we measure these bond association energies, we can take, for instance, C2H6 giving us C2H5 plus H, right? And we could measure the rate of formation of ethyl, right? If we do that, we can then get the activation energy for that reaction if we do it at different temperatures, okay? And then we can get the bond dissociation energy or the heat of formation of an ethyl radical, okay? because we'll know the others, okay? So in this case, in this way, we can get tables of bond dissociation energies from kinetics, okay? Okay, and just to say then, I talk about Arrhenius, right? We have the rate constant is equal to A e to the minus EA over RT. But there are other ones. So the vapor pressure, the Clausius-Clapeyron equation is very similar. You have P over P infinity is the exponent of minus the heat of vaporization all over RT, okay? You have viscosity is the Andrade formula. You have